Thanks for the introduction and thanks for sticking to the last lecture. So last time we discussed tensors, and I told you about this important notion of tensor rank and how it can be used kind of a measure of entanglement, given that a tensor is rank 1 if and only if it's separable. So the higher the rank, the more entangled the tensor in some way, in some mathematical way. But now let me discuss a much more useful measure of entanglement for pure quantum states, which is this injective norm. And this will be the first example of a tensor norm in this lecture. It comes in the third lecture, but we'll discuss this example and then go into the more general theory of tensor norms. Okay, so what is this injective tensor norm? So the setup is as usual. I have a state, a pure state psi, which lives in a tensor product of Hilbert spaces, K Hilbert spaces, and its injective norm, or the epsilon norm of psi, it's defined as the maximum overlap of psi with product tensors. Okay? So it's the supremum over all these vectors phi I of norm 1 of the scalar product between psi and the tensor product of the phi i's. So this is the definition. You can show that it is a norm. It is indeed a norm. It satisfies all the axioms, triangle inequality. And why is this nice? It's because you see, basically you can see very easily from the Cauchy-Schwarz inequality that this is always smaller than 1, this norm, and it's 1 if and only if these two vectors are aligned. So basically it's 1 if and only if psi is a product vector, so it's separable. So this injective norm, it satisfies psi is 1 if and only if the vector is separable. And if you cannot decompose psi as a tensor product, then this injective norm will always be smaller than 1. And then this is strictly smaller than 1 if and only if the state is entangled. Okay. So this is this way of thinking between as the maximum overlap with product vector. You can also think of distances. So if you compute the norm of the difference between psi and a product vector, then since both these guys are on norm 1, you just get 2 minus 2 times the overlap. So you can also think of the injective norm as measuring the distance between your tensor psi and the set, this manifold of separable states. Well, I mean, 2 minus the square of the injective norm. Okay. So this injective norm measures the distance to separable states in a way. Now, let's look at the bipartite case. So as always, with all tensor problems, we look at the bipartite case because this is always the easy case. So in the bipartite case, so I have this psi which lives in a tensor product CD tensor CD. And so the injective norm, it's the same. It's the maximum overlap between psi and product vectors. And now if you think as, in the last 2 days, as psi not as a 2 tensor, so not as an element here, but as a matrix, we have seen several times that CD tensor CD and D by D matrices are the same thing. Then you can write this as the supremum of alpha capital psi, the matrix version of small psi, and beta. So instead of, so this alpha tensor beta becomes these 2 vectors. Now basically here you recognize, when you sup over alpha beta, you recognize the operator norm of the capital psi. Or if you like to think in terms of vectors, it's the largest Schmidt coefficient of your vector. Okay, so if the largest Schmidt coefficient, so let me, maybe it's useful to recall this. So this psi, you can write its Schmidt decomposition. Where these numbers, you order them usually. And then the injective norm of this psi is just a square root of lambda 1. So the largest Schmidt coefficient. Because these numbers are normalized such that sum of lambda I equals 1. Okay, so for bipartite vectors, you get the largest Schmidt coefficients. In the bipartite case, of course, we have much more natural and operationally defined measures of entanglement, such as the entropy of the Schmidt coefficient vector. But in any case, here we get the largest one. So you see, if the largest one, this largest Schmidt coefficient is at most 1, and it's 1 precisely when you have only one Schmidt coefficient, so when your state is separable. Okay? And in a moment, we'll see that this injective norm is a special case of these tensor norms. So we'll see it as in this framework. So one important question here. You can check, for instance, you can check or you can compute them for now for the tensors that you prefer, like the GHZ or the W state. And you see whenever you have to compute this this injective norm, you have to solve this optimization problem. You have to soup over all the vectors phi 1 up to phi k. And sometimes this is easy, sometimes this is hard. It depends on the vector you study. Actually, in the physics literature, we see not this injective norm, but something which is almost the same thing, this so-called geometric measure of entanglement, GME, which is defined as the minus log of this this injective norm squared. So you see in that bipartite case, you get a minus log of lambda 1. So it's like this infinite Rényi entropy of the state, but it's kind of, it looks more like an entropic thing, so it's something which is additive because of the log. And again, it's the same idea. So this geometric measure of entanglement is minus log of that number squared. It's it gives you a measure of how separable or entangled the state is. And there is this very nice paper about the properties of this geometric measure of entanglement, or equivalently the property of this injective norm, like many interesting properties. So it's a very good reference for this injective norm. Okay, good. Now let's talk. Now we switch gears. We go back to abstract world, and we talk about tensor norms. So let me introduce what tensor norms are. So the idea is with tensor norms is that you have two vector spaces with a norm on each one, and you want to construct somehow a larger. You want to put these two pieces together. For example, if you have two norm spaces, so on the direct sum, a direct sum is just pairs of elements, one from X, one from Y. You can define several norms, right? You can take, for instance, the maximum of the two, or the sum of the two. There are many possibilities, and you get different objects. You can ask the same questions for the tensor product of two spaces. So duality will play a key role here. So remember this dual space. So every time you have a vector space, it comes with a dual, and this dual space is just, the vector space is the linear forms on your vector space, and the norm of a linear form, so the norm on this dual space, it's defined like this. There is no typo. So it's the supremum over all vectors in your space of phi of x. So every norm space comes with a dual. And this is the definition of a tensor norm. So a tensor norm on X tensor Y, it's a norm. I will denote it by just norm, such that it matches the norm on X and the norm on Y when I look at simple tensors. Okay? So if I have a simple tensor, an X tensor Y, then this norm of X tensor Y is just the product norm X of X and norm Y of Y. So this is something very natural that you would like to impose. And actually, it makes a lot of sense to impose also the dual condition. You want the same thing to work for dual spaces. So this norm on X tensor Y comes with a dual norm that denote norm star. And I ask that the dual norm of a simple tensor product of linear forms, it matches the things you have on your tensor factor, right? So these are kind of like compatibility conditions. You want the norm, this tensor norm to look as the initial norms when you have just product tensors. Okay? Of course, now the interesting part comes from the fact that you have tensors which are not product tensors. All right. Yes, question.
And second, obvious from the first, like is like if there is a there's a norm on x, there's a norm on y, there'll be a dual norm on x which will be x star, there'll be a dual norm which is x star y, and
Yes, these are these ones.
and if first condition is satisfied, does it
No.
shouldn't that imply
No,
that
no, you have to require them. It doesn't. So you have to require also this condition. No, I don't. I don't think so. We can. I think not. I think not. So you need to require these two conditions. But we can discuss about it. Maybe. Let's discuss about it. But I think you need both. Okay. So here's an example. So for the first space, take real numbers with Euclidean norm. Second space are n with the Euclidean norm. So this is the tensor product vector space. It's just R n times n. And actually this L2mn norm, so the 2 norm on this bigger vector space. So now forget that this has a tensor product structure. Forget about it. It's just big vectors of size mn. So this L2 norm on the bigger space is actually a tensor norm. Why is this? Because if you compute the 2 norm of a tensor product, have this formula, and basically factors. I mean, nothing more to say. And since this is self-dual, it's also the dual version. So the L2 norm is self-dual. Remember, this P norm is dual to the Q norm, where P and Q are conjugate. So this 2 norm is self-dual. So the second one comes for free because of the self-duality. So this L2mn norm, it's a tensor norm with these two spaces as factors. Nothing very surprising. Now this is the main definition. Maybe the most important definition from this series of lectures. So among these tensor norms, there are two which are very special. One is called the injective, and the other one is called the projective tensor norms. So here are the definitions. So I have two spaces, x with a norm and y with another norm. And this is a norm on the tensor product. So I have an arbitrary tensor z on the tensor product. And its epsilon or injective norm is defined as the supremum over, this is a typo, it should be capital X, the supremum of all linear forms in the dual balls. So alpha, the norm of alpha in the dual norm of x is smaller than 1, the same for beta, of alpha tensor beta evaluated on z. Okay? So I'm evaluating my vector z on tensor product of linear forms of norm 1 or smaller. Okay. And the projective one, it's defined again as an optimization problem. It's an infimum this time over all decomposition of my tensor as simple tensors, as a sum of simple tensors. So here I just give the definition for 2, but you can see it extends in the same way for more tensor factors. So I look at all decompositions of Z, and I'm minimizing the sum of the products of the norms of the elements appearing in the decomposition. Okay. So one can check that these two are indeed tensor norms. And well, I mean, we call this new space you have, so X tensor Y equipped with the epsilon norm, for instance, we call this the injective tensor product of these two spaces, and the same for pi, the projective. Okay, so you see these two are defined in very different ways. I mean, but kind of remember that they are both optimization problems. One is a max, one is a min. Okay. Yes? So this is Grothendieck has introduced these things. Before he turned to more algebraic geometry, he worked on Banach spaces. I don't know. I thought I knew, but I don't remember. No, I don't know. We'll have to check his original paper. He introduces much like a bunch of tensor norms. Sometimes also they are called the min and the max for a reason that will be clear in a moment, but people still call it injective and projective. But I don't, so yeah, sorry, I don't know. Ah, good. Yes. Yes. Well, Z is the tensor you want to compute the norm of. So this is how you define the norm of Z, the injective norm of Z. You're,
is it same as the one in projective tensor norm? Z was in projective tensor norm. Z is sum over all extensor y.
yeah, Z is an arbitrary tensor.
Is this it's the same as above?
Yes.
Oh, okay.
So Z is an arbitrary tensor, and you're optimizing this. You're maximizing over the set of all alpha and beta the scalar product, this evaluation. I'm not taking dot products between x and y. Here I'm taking dot products between Z and dual elements.
I'm talking about projective.
Here there is no dot product.
No, is that why it's called projective?
I don't know. I still don't know why it's called the projective tensor norm. But here x and y, I mean, x and y are different, are apples and oranges. You cannot mix, I mean, you cannot take dot products between them.
Okay,
basically, you want to decompose this Z in the most economic way with respect to this quantity.
Thanks.
But yeah, I'm sorry, I don't know how these names came to be. Okay, so now we look at a bunch of examples because this is a bit too much. It's a bit too abstract. So let's look at operators T between two spaces. So I have an operator T between X and Y. I can always define this, what is called the induced norm, as the usual thing. You know, I'm taking the maximum of the norm of T of X over all X's of norm smaller than 1. Okay? So this defines a norm on the set of operators between X and Y. So here you see the two norms appear. So this is the unit ball in the original space. And of course, in the output space, I'm taking the Y norm. Yep. Okay. So remember, again, we're always using this fact that the space of linear maps between X and Y, it's the same thing as the tensor product, so as vector spaces, as the tensor product between Y and the dual of X. Okay? Because what is a linear map? A linear map is something which eats something from X and gives you back something from Y. So let's look at, again, let's look at this formula through this prism of tensor norms that we just learned. So the sup of X of the Y of the norm of T of X in Y. So this quantity, the norm of T of X in Y, I can write it via duals, right? Because, you know, in any space, the norm of Z is the sup this is alpha of smaller than 1. Okay. So here I'm just writing this norm of Y using the dual space. So it's the streamer over all linear forms beta in the unit ball of Y star of this scalar product. And now if you see T not as a linear map, but as an element of this tensor product space, this scalar product here, B and T of X, is the same thing as beta tensor X scalar product with T. So now you see, now I see T as an element here. And now, of course, you recognize exactly the injective norm of the injective tensor product of Y and X star, because you see here I'm taking the supremum over all X in the unit ball of X. So here I should take a dual, and the same with Y, I should take the dual of Y star, which is Y. Okay. So just playing with this duality, this induced norm is nothing else than an epsilon. So every time you see the norm of an operator, you have to think that this norm is the epsilon, is the injective tensor product of two things. The one on Y and the one on the dual of X. Okay, so this is just rewriting stuff. Huh? There is no computation done here. Okay, this is the same thing said again. Now, in particular, remember the operator norm. It's just the induced norm from L2 to L2. So you do the same computations. It's this induced norm from L2 to L2. It's the same as the injective tensor product between L2 star and L2, but L2 is self-dual. So the operator norm of a matrix, it's the same thing as the injective norm of this matrix seen as a tensor. So operator norm is equal to the injective norm with L2s. Okay? So this is the idea that whenever you see Mn, think of Mn as Rn tensor Rn, and the operator norm is built using this injective tensor product. Same story with the trace norm. So the trace norm, remember, it's trace of absolute value of A, or the sum of the singular values of A. We shall see that, let me prove that this trace norm is the projective tensor product now of L2 and L2. Okay. So you can start with the polar decomposition. Yeah, maybe I can just skip the proof because it's a kind of straightforward and I don't want to spend too much time on this. Okay. So this is very important. So the most important norms on matrices, the operator norm and the trace norm, are actually special cases, the most simplest special cases of these injective and projective norms when you have L2 spaces. Now, you can do more exotic examples. For instance, if you want to look at L infinity n injective tensor product with some arbitrary space. Let's have a look at this example, maybe because it's kind of new. So what is this injective tensor product? So first, what is the vector space? The vector space is just Rn tensor x. So vectors in Rn tensor x, I can just write them using a basis of Rn. This is the computational basis. So they can be written as sum of I tensor xi, right? So basically, you can think of that just these vectors xi stacked one on top of the other, right? So here xi are vectors in x. Okay. So let's compute this injective norm. What is the injective norm? It's the supremum over elements in the duals, linear forms on Ln and linear forms on x, of alpha tensor beta comma x. So so the dual of L infinity is L1. What are vectors in so here you see I have to take the supremum over all linear forms in the unit ball of L1, but the extremal points, let me write this here. So the extremal points of the unit ball of this L1n, actually these are just the plus minus EI. Remember, when we talked about these LP spaces, I told you that the extremal points of L infinity were these plus minus 1 vectors. So these are the cubes. So they are the 2 to the power n vertices of the cube. And for the dual, we only have 2n extremal points. And these are the plus minus EI. So remember, in n equals 2, this is the unit ball of L1. So this is the unit ball in one space. And you see the extremal points are these 4 vertices. Okay, so these are plus minus the basis. So basically the supremum over alpha is just a supremum over these 2n elements. So there is a sign and a component. And when you when the sign doesn't matter, you just put the absolute value because the sign will allow you to choose the sign of the scalar product to make it plus. So this gives you the absolute value. And EI, so when I take this EI tensor beta comma x, this EI will select, this is ket I, right? So it select the vector xi. So you get this number here, the supremum over all betas of beta and xi. And the same story, when I take the supremum over beta in the unit ball of the dual space, I get, yeah, there's a typo here. I get just the norm of xi. So this is not a dual, this is a dot. So the answer, this injective norm is just the maximum over all the vectors appearing in X. The maximum over all I of norm of xi in the space X. Now this is one example when you can actually compute this. Now, a very important result, it's again about duality, so duality, as I told you, plays really a fundamental role, is that if I take this injective tensor product of two spaces and I take the dual, then the result will be the projective, so injective goes to projective, the projective tensor product of the dual spaces. Okay. So dual of the injective tensor product is the projective tensor product of duals, and vice versa. So this is something very useful, these duality relations. And now we come to this theorem which tells you that, it tells you why these injective and the projective norms are so special. It's because any norm on the tensor product, which is a tensor norm, so which satisfies these two conditions at the beginning, must lie between the injective and the projective. Okay. So any norm which, so here there is an if and only if. So a norm on X tensor Y is a tensor norm if and only if you have these inequalities. If it lies between the injective and the projective. Okay. So the injective one is the smallest possible tensor norm, and the projective tensor norm is the largest. So let's look at some implications. One is very easy. Why is the projective norm the largest one? Well, take some decomposition of your tensor Z as sum of xy tensor y, which gives you the projective norm. So this decomposition is such that the projective norm is equal to the sum of the products of them. Okay? Now look at this other norm, this Z norm, this arbitrary tensor norm of Z. Well, I'm replacing Z by this formula, and I'm just using the triangle inequality for the tensor norm here. And here I'm using that for simple tensors. Any tensor norm gives factors as norm of xi and times norm of yi. And I get back to pi. So you see, it's really that simple. I mean, this inequality. And the other one, it's kind of the same thing, but dualized. So the scalar products, remember in the injective norm, I have this scalar product with linear forms in the dual spaces. So this the scalar product is smaller than the product of this in the dual space times Z in the primal space. And now this is a simple tensor, so the norm factorizes. This is the second property from these from the definition of a tensor norm. And now these are in the unit balls, so they are smaller than 1, so I get back norms. So this was the state. So these are really, I mean, you can think that these have been conceived such that they're really tailor-made to satisfy these inequalities. Now, back to the first thing we discussed. We discussed this injective norm for multipartite entanglement, right? So remember, this injective norm of psi was the supremum over psi against the overlap of psi against with these tensor product vectors. And now you recognize that this thing is nothing else than the norm of psi with respect to the injective tensor product of L2 spaces, right? Because this condition here corresponds to the vector phi I living in the unit ball of the L2s. And I have a supremum of an overlap, so this is precisely how this epsilon norm is defined. So this injective norm for tensor is nothing else than the norm of psi in L2, injective L2, injective L2. And you can see that this injective norm is smaller than the L2 norm of psi, because so before that, the L2 is a tensor norm. So since the epsilon one is the smallest tensor norm, then you have this equality. The L2 norm of psi is 1 because psi is a quantum state, so you always have this inequality with equality if and only if the state is separate. So now you can see directly why, where does this injective, this epsilon norm comes from. It's just the injective tensor product of the L2 spaces corresponding to each tensor factor. Now here's a very nice question, which is largely open. So I told you that this injective norm of a vector is 1 if and only if the vector is separable, and generally smaller than 1 for entangled vectors. So you might, what is natural to do is to look for the vector which has the smallest injective tensor norm. So this will be the vector which is the farthest away from the set of separable states, and you can argue that this is the pure state which is most entangled. So what are those? Find the most entangled pure quantum state for an arbitrary number of factors and arbitrary dimensions. For instance, when you only have 2 factors, we know that this is the maximum entangled state because we can actually compute this epsilon norm. You know, we know that it's this square root of lambda 1, so you want to minimize square root of lambda 1, and the minimum possible is 1 over d when all the Schmidt coefficients are equal. So for k equals 2 is simple because it's a matrix problem and we have these singular values, but in general for k larger than 3 we don't have singular values. We don't have formulas for these psi epsilon, but nonetheless it's interesting to compute them, to compute the most entangled pure state in arbitrary dimension, an arbitrary number of factors. And this is largely open. It has only been solved for small k and small n, small d. So I think it's a very nice question. Okay. Now let's discuss mixed states. So up to now we have only discussed pure states. Let's discuss mixed states. So mixed states or density matrices are positive semi-definite matrices which have trace 1. Okay? So I would denote this set by MD1 plus, 1 for trace 1 and plus for the fact that they are positive semi-definite. Oops, typo. And you know, one way to think about this is that this is kind of a non-commutative version of probabilities, right? Because probabilities also have kind of, the probability simplex has kind of the same definition, just numbers which are non-negative and sum up to 1, but you have somehow different notions of positivity here. Okay, this is positive semi-definite, this is like entry-wise positive. And okay. So a density matrix is called separable if I can decompose it as a convex sum of product density matrices, right? So if I can decompose my density matrix rho as a sum over I of Ti, these are probability weights, times rho 1, tensor rho 2, tensor up to rho k. Okay. So if I can decompose it as a sum really of these simple tensor products. And here, of course, the important condition is that these matrices rho I should be density matrices, so should be positive semi-definite. Otherwise, if I don't have this condition of positive semi-definite, rho being an element in this space, of course I can find a decomposition as such, because any tensor can be decomposed as such. But now I'm imposing the extra conditions that every factor here, every matrix appearing in this decomposition should be positive semi-definite. Okay, so what I will try to do next, and you will see this will be a very useful thing to do, is to to characterize separability or entanglement using tensor norms. As we did for pure states, we want to do the same thing for mixed states. And you see again, the trouble here is that the definition of separability is kind of about positivity, right? I want to find a decomposition of my tensor such that all the factors are positive. So how to transcribe this condition of positivity in terms of norms? That's the question. And remember, we did this when we discussed the trace norm. Given a self-adjoint matrix X, I can characterize the positivity of X using the trace norm in the following way. So X has a spectral decomposition, sum of lambda I, projection on AI. The trace norm of x is the sum of the absolute value of the eigenvalues. The trace of x is the sum of the eigenvalues. So these eigenvalues are all non-negative if and only if the one norm is equal to the trace. It's something very trivial, but it allows us to write this positivity condition in a metric way in terms of the norms. Okay, so if I want to talk about so this thing in the multi-partite setting says that rho is a positive semi-definite matrix, the density matrix, if and only if the one norm of rho, so the one norm in this big space, right? So here the one norm doesn't know about this tensor product structure. It just is a matrix of size d1 times d2 times up to dk. This is a big matrix. So rho is positive semi-definite. Again, this notion of positive semi-definite doesn't care about the tensor product. It's just a big matrix. So if the norm of rho in S1 of this huge space is equal to the trace of rho. So this is positivity. Okay? Now I want to ask about separability. I want to ask, now I know that rho is positive. Can I decompose rho as a sum of tensor products of positive elements? That's the question. So now, of course, the tensor product structure should come in play because the definition is about this. And here is the result. So rho is separable if and only if the projection tensor, so the projective norm of rho is equal to its trace. And here it's the projective taken either between the S1, so the matrices with the trace norm, or self-adjoint matrices with the trace. Sorry. Okay. So I'll this S1D, it's matrices with a trace norm, and if I write self-adjoint after the one, in that now I'm looking at self-adjoint matrices with the trace. Okay. So you see this is very nice if you compare this quantity with these ones, because positivity is just about the S1 norm of the big space, and separability is about these tensor norms, so these tensor norms which know about the decomposition of my space in a tensor product. So I have to take the projective tensor products of all these S1 space. So let's see. Okay, good. So let's look at the proof of this. First, let me just write rho pi and rho pi self-adjoint to denote these projective norms, such that I don't have to carry this horrible notation. So let's show 1 implies 2. So one was rho separable, and 2 was that this norm here is equal to 1, or to the trace of rho. So rho is separable. It means that I have a decomposition with positive rho i's. Right? So the projective norm, remember, it's an infimum over all decomposition of something. So let me take this decomposition. So it's upper bounded by this particular decomposition. And what I'm minimizing is the sum over norm of this times norm of each tensor factor, right? So the norm, let's look at the norm of each factor. So norm of Ti rho I, since this is positive, and Ti is also positive, this is a positive semi-definite matrix. So it's one norm, it's equal to its trace. The trace of this, rho is of trace 1, and I just get Ti. And all the other ones are just density matrices. So I get Ti, and I get sum of Ti's, which is 1. Remember, the Ti's were probability weights. Okay, easy. So yeah, so sorry, this shows that the projective norm is smaller than 1. But remember, the projective norm is the largest tensor norm. This one is a tensor norm. So it's larger than the one norm of rho seen in the big space, which is equal to its trace, because rho is positive, so it's 1. So we get the other inequality. Okay, so we show that rho separable implies that this projective self-adjoint norm is 1. Now, 2 implies 3 is easy because, so remember, 2 was about the self-adjoint, the projective self-adjoint, and 3 was about just the projective norm of S1 spaces. But so what does the self-adjoint, what's the difference that the self-adjoint makes? Remember, let me show you again the definition of the projective norm. So remember, the projective norm was defined as a supremum over, as an infimum over all these decompositions. So if I allow self-adjoint matrices or all matrices, so if I allow all matrices, let's say xi, then of course I have more possible decomposition than if I allow only self-adjoint matrices. So the projective norm without the self-adjoint will be smaller because I have more decompositions. So the projective norm without the self-adjoint is smaller than the one with self-adjoint. We know that the other one is 1. We know that this is larger than, as before, than the trace of rho, which is 1. So they are all 1. Okay. Now, this last implication is the interesting one. So how to go from this metric property of the projective norm being 1 to show that rho is separable, so to build a decomposition. Okay. So let me start. So I know that the projective norm of pi is 1. So it means that I have a decomposition which gives 1. So there is a decomposition of rho as sum of ai1 up to ai should be a k, such that the sum of the products of all these norms is 1. This was the definition of the projective. So I have such a decomposition. Of course, this is not a separable decomposition because these are arbitrary matrices. They don't have to be positive. So what I want to show is that somehow I can tweak a bit my decomposition in order to make these matrices, these factors here, to be positive semi-definite. And this is what we will do. Okay. And this will follow from some equality cases in this big inequality. So rho is a density matrix. 1 is trace of rho. Trace of, using this decomposition, the trace of rho is the sum over I of the product of the traces of the factors. The trace is smaller than the absolute value of the trace, and the absolute value of the trace is smaller than the 1 norm. And I know because the projective norm of pi is 1, then this quantity is 1, because these are the matrices which achieve this one in the infimum. Okay, so basically I have this chain of equalities with 1 and 1 at the end, so I have equalities everywhere. And from this I can get many things. For instance, from this inequality here, which is the one which goes from this guy to this guy, so it's this one. I know that my matrix AIX is actually some phase WIX times a positive semi-definite matrix. So then if I pull up all these phases together, then I can write rho as a sum over I of some phase times a tensor product of positive semi-definite matrices. And now again, you just have to take care of this omega I. Again, from these equality conditions from the first one, you can show that the omega I is positive. So basically, you can this will be your you can pull the TI from, you can normalize these matrices BI to have them trace 1, so to become density matrices. And the factor you get with the omega will give you the T, the probability weights. Okay, so the idea is that the fact that the projective norm is 1, it's the smallest possible value, implies using some equality conditions that the optimal decomposition for the projective norm is the separable decomposition of your quantum state. Okay. So this ends the proof. Okay. So this is what we have done. What we wanted to, we have achieved what we wanted at the beginning. We have a characterization of separability as in terms of the projective tensor product of this S1, these trace norms, these S1 spaces. Now I'm using again and again the same old trick that S1, it's a matrix space. So S1 itself is a tensor product, is a projective tensor product of two L2 spaces. So I have the final form of my separability characterization in terms of tensor norms, that a state rho is separable if and only if this projective, so I have pi's everywhere. This is associative, I didn't tell you, but these operations are associative, so I can even drop the parentheses. They are just here to illustrate that this first parenthesis corresponds to the first S1 space, the second one to the second S1 space, etc. So I have that rho is separable if the projective norm of rho of these, now I have two K spaces, I have two of size D1, two of size D2, etc. This is equal to the trace of rho, or to 1. Okay. So separability is as easy, quote unquote, as computing these projective tensor product of 2K Euclidean spaces. Okay, good. So I just have, for now, I just have an equivalent characterization. How does this help me do anything? I just introduced some complicated objects to talk about separability. Why is this useful? Many reasons. Here's one. So turns out that if I give you the density matrix and if I ask you whether it's separable or not, so if I ask you to find the separable decomposition, this is an NP-hard problem. It's hard to decide whether a state is separable or entangled. So what do? People have introduced these entanglement criteria. These are just some conditions which are actually easy to analyze and to run on a computer, which can prove either separability or entanglement. Here I've been focusing on entanglement criteria. So of course, since they are like efficient, they cannot do both things, so they have to be only one way. So the most famous one is the positive partial transposition criterion, or the PPT criterion, which is the simple observation that if I have a state rho that is separable, then its partial transposition, which is defined as I'm acting, so rho, have a picture, maybe. So what is this partial transposition? Right, so rho is a bipartite density matrix. It has two inputs and two outputs. And the partial transposition does nothing on the first space and transposes the second legs, the legs on the second space. Okay, so this is this, I'm acting with the identity on the first tensor factor and with the transpose on the second one. All right, and the criterion says that if rho is separable, then this new matrix I get, this rho partial transposition, then this is positive semi. Okay, this is denoted by rho gamma, because you can see gamma is half of the t, the second half of the letter t. Good. So actually, in practice, people are using the opposite statement, is that if the partial transpose is not positive semi-definite, so if it has some negative eigenvalues, then this guarantees that the state rho is entangled. Okay. So this is this graphical representation of the partial transposition. I'm swapping the bottom legs. And if you prefer coordinates, it's just saying that the coordinate IAJB of the partial transposition, I'm just transposing the A and the B. I'm keeping the I and the J in place, and I'm swapping the A and the B. So this is rho IB JA. So you're just transposing one set of coordinates. Okay, this is very easy to prove. Why is this criterion true though? So if my state rho is separable, then I have a separable decomposition. I can write rho as sum of alpha I tensor beta I, where these are positive semi-definite matrices. And the partial transposition of rho is, as I told you, I'm just transposing the second factor. And the transposition of a positive matrix is still positive. So here again I have a sum of positive semi-definite matrices. So I get the positive semi-definite matrix. So it's a very simple observation, but it's really the criterion which is most used in practice. One of the nice things about it is that so when the dimensions of the Hilbert spaces are small, meaning it's either 2, 2 or 2, 3, this is equivalent to separability. So we have an equivalence in the implication above. But if the dimensions are larger, so already for 2 times 4 or 3 times 3, there are states such that they are entangled and still this partial transposition is positive. So we say that the criterion fails. It doesn't properly detect entanglement. Okay. So this is this PPT criterion. Here's another one, the realignment criterion. The second most famous entanglement criterion. How does this work? It's kind of the same idea. If rho is separable, then the one norm, this implies that the one norm of some matrix called rho realigned, so rho R, the trace norm of this matrix should be smaller than 1. So what is this realigned matrix? Well, it's kind of the same story as the partial transposition. You have to swap 2 legs. But now I'm swapping different legs. So it's this leg here, the first input leg, and the second output leg that are being swapped. Okay, so IAJB, I'm swapping, let's see, I'm swapping the first input leg, so this is the J, and the second output leg, this is the A. So the realigned matrix coordinates IAJB, it's the original matrix rho coordinates IJAB. Okay. So graphically, it's easier to understand. I'm just swapping these diagonal legs, whereas remember for the partial transposition, we were swapping here. We can try to prove this. It's not very hard. Maybe one important observation is that when you do this, when you do the swapping of legs, the resulting object here, this matrix here, is not self-adjoint anymore. It can even be rectangular, because if I have different dimensions on top and on bottom, then the final dimensions will be, if I have D1 here and D2 here, then the dimension here will be D1 squared, and the dimension here will, the dimension here will be D1 squared, and the dimension here will be D2 squared. So this realigned matrix is kind of it's rectangular in general, but yeah, of course, I can still compute its one norm. Good. Okay. So why I'm telling you about this? Because they appear very natural when you think about these tensor norms, these entanglement criteria. Okay. How do we understand this? So remember, we have bipartite density matrix, so it has 2 inputs and 2 outputs. And we know that rho is separable if and only if this projective tensor norm with 4 spaces, I have an L2 space on each Hilbert space, is smaller than 1. It's 1. So something that I didn't tell you is that whenever you try to compute, whenever you take the simplest possible space, the L2 space, and whenever you want to compute the projective or the injective norm of k copies of L2, this is again an NP-hard problem starting from k equals 3. There is this very nice paper called All Tensor Problems Are Hard, or something like this. There are many problems which for matrices they are very easy. You just compute singular values and do something with the singular values. For tensors, they become NP-hard, and already at k equals 3. So here, of course, this is very bad because we have 4 copies of L2. So what do? We know how to do the projective tensor product of 2 copies of L2. We have seen that this gives you the trace norm. But we have 4, so we are in trouble. And an idea will be, okay, let's package some of these 4 spaces into 2 groups of 2. Okay. So I will, maybe I should write it here. I should have written it down. So I want to compute I want to compute this tensor norm. So I know this is hard because I have 4 tensor legs. And what can I do? I can package, let's say, like this. And I can say that this is larger than. And here I would like to replace this space with a different one, with a norm which is smaller. Okay? So since this is the, so for instance, I can choose, let's say, so maybe D1, D2, D3, D4. I can choose this one. Why is this? This is because the norm of some Z L2 projective L2, let's say D1, D2, this is, it's larger than the norm of Z, but I just take the L2. Okay? Because the projective norm is the largest one, particularly it's larger than just the Euclidean norm of on the big space. Okay? So I say that this norm is larger than this norm is larger than this one, so the projective is larger than the projective, and now I have something that I can compute, because I have just 1 pi. So the idea is to kill 2 of these projective tensor products, which makes the problem NP hard. And now the question is, how do I pair? Well, there are 3 choices, 4 choose 2. So let's look at them one by one. The first choice is to pair input 1, input 2, and output 1, output 2. Let me draw it again so that you can see it. Row. So this was in 1, out 1. And this is the in 2, input space 2, output space 2. So I'm pairing the inputs together and the outputs together. And I'm saying that the projective norm, this big norm, so I'm just writing this inequality that I wrote here. It's larger than rho, and here I have D1, D2, and D1, D2, right? Because this has dimension D1, this has dimension D2, okay? So when I put these two things together, I get a big L2 space of dimension D1, D2, and here I get a big L2 space of dimension, again, D1, D2. And I have a projective norm, so L2 projective L2 is just the S1 space. So what I get back is simply the trace of rho, because rho is positive semi-definite, which is 1. So I have shown that the projective norm is larger than 1, but this I already knew. It's a trivial thing. Projective norm is always larger than the trace, which is 1. So this was a very bad choice. Let's look at the second one. Well, it's very bad. It just gives you something trivial. Now, I will pair in the input 1 and output 2, and output 1 and input 2. So if you do this, again, you have L2 spaces, but I have to show you which L2 spaces we're talking about. So what am I doing? So I'm saying that so this is the case 2. So what I'm pairing, I'm saying that the projective norm of this with 4 spaces, this is larger in case 2. Then the projective norm of rho, let's see, I'm input 1 and output 2. And well, what's left? So L2 tensor L2. So I think dimensions are D1, D2, and D1, D2. Okay? So instead of seeing these two legs as separate legs, I'm seeing them as one big leg. So I merge them in one big leg. So what I'm left is it's with a matrix which goes from D1, D2 to D1, D2. And you recognize that this is exactly the partial transposition of rho, if you look at how the legs go. Okay, because all I've done is just swap these bottom legs. Okay? So I have shown this thing. I have shown that the projective norm of rho is larger than the one norm, the trace norm of the partial transposition. And then this is something I can compute, right? Because I can compute one norms, sum of singular values, whereas this one I cannot compute. But what I claim is that this is exactly, we have recovered the partial transposition criterion. Why is that? It's if this number here is larger than 1, then the projective norm is larger than 1, so rho is entangled. But this S1, this trace norm of rho gamma is larger than 1. It's the same as rho gamma being non-positive semi-definite, because trace of rho gamma is still 1 by the same trick where the one norm tells you about positivity. Okay? So just by saying that I want to simplify this tensor product of 4 L2 spaces, this projective product of 4 L2 spaces, I want to simplify it by killing 2 of the projective tensor products. I get back my PPT criterion without any need for tricks or, you know, this shows that kind of this is not as ad hoc as you might think. Now, the case 3, the final possible pairing. How does this work? It pairs input 1 and output 1. So again, that norm, projective norm, is larger than, let's see. I'm pairing input 1 and output 1, and input 2 and output 2. Okay? Meaning that I'm forgetting that these two legs are separate, they form a tensor product. I just say that they form a big L2 space. So this is L2, let's see. Well, I mean, it's D1 squared, tensor projective D2 squared. Right, because these have dimension D1 and these have dimension D2. And I get back exactly this real-line matrix. If you think about the legs, how the legs work in this matrix, you will see that these are precisely the way I permuted to get the real-line matrix. And same story, if this number now is larger than 1, this implies that pi is entangled, as before. So we get back the real-line criterion. Okay? So the moral of the story is that you can, just by playing with these projective tensor norms, so you have this problem which is, in general, you have to compute this very complicated tensor norm of 4 spaces, and by grouping them in smart ways, you can get for free these entanglement, this very well-known entanglement criterion, which were found way before. I mean, people thought about tensor norms in quantum information theory, and so I think this is kind of nice that you can get those for free. Okay, but this was about recovering old results. What can we do? Can we do something new with this? So let me tell you about some work that done with Cecilia Lancien and Maria Givulescu about entanglement testers. Okay? So it's the same idea as before, using this kind of pairing of these spaces in order to reduce the number, to reduce the complexity of the problem, so to reduce the number of projective tensor products. But kind of this idea like generalized to not to bipartite states, but to multipartite states. And before, what we did, we're just playing with the legs, right? We're moving the legs left and right. We're swapping the legs. But actually, you can do a bit more. You can apply some linear maps. So, so this is kind of the intuition. Let's see how this works in practice. So now I'm going to consider. I'm going to consider multipartite mixed density matrices. So I have density matrices with k inputs and k outputs. And as before, you know, we have the same result, that separability of rho is characterized by this projective norm given by S1 spaces, by Schatten class. Okay. So this is a definition. A map from MD, So here, small d, so from a metric space to a vector space, capital D can be anything in relation to the small d. It's called a tester, a linear map is called a tester. If it has S1 to L2 norm smaller than 1, meaning that it sends matrices of trace norm smaller than 1 to vectors which have Euclidean norms smaller than 1. Okay, so I require this contraction property with respect to the S1 to L2 norm. You will see why I do this. Because of this inequality here. So first, let's not look at the inequality. Let's just look at what we are doing. I'm going to apply these TIs, these map TIs, one for each leg of rho to my density matrix rho. So how does this work? You see, T1, it's a map which takes a matrix space as an input. So it takes two wires, one input and one output wire, and it gives back a vector of size d. Maybe, I don't know if this wire is supposed to be thicker than this one. So these wires here have dimension capital D, and the wires here have dimension D1, D1, D2, D2, D3, D3. And here I have these. It's written here. So these testers, why do we call them testers? Is like this, this device that you use to measure, voltage or resistance. I mean, this thing with two things that you put on your circuit and it displays a number. So this kind of, you hook these T's to your density matrix and you get a multipartite vector, actually. You get a tensor, right? You don't have a matrix structure anymore because my T's go from matrices to vectors. So when I apply 3 testers on my 3-partite rho, I get a 3 tensor. And why is this interesting? Well, from the following simple reason is that the norm of this output, this guy here, if I look at the L2 tensor projective L2, norm of this, because of how I normalized my testers, this is the definition of testers, this will lower bound the projective norm S1, projective with S1 of X. And remember that for density matrices, this is the thing that characterizes separability. So this being 1 characterizes separability. So from this inequality, you will see that I get again an entanglement criterion. If this number here is larger than 1, then this will be larger than 1, and the state will be entangled. And why do we do this? Because this beast here, you see it has just 3 legs, can be much simpler than rho to begin with, right? Because to begin with, rho had 6 legs, this has 3 legs, and depending on the maps, these TI maps, this can be, for instance, I can take the TI maps to be 0, but then of course I will get 0 here, so this will be useless as an entanglement criterion. But if I choose the maps TI in a nice way, maybe I can get entanglement criterion. And let me show you some choices. Yeah, so this is what I just said, that if this number here is larger than 1, then this will be larger than 1, so rho will be entangled. So let's look at some testers. The first one, the easiest map which goes from matrices to vectors, it's this vectorizing operation or flattening or however you would like to call it, which takes a matrix and puts it into one big column, right? So it puts the columns of the matrix one on top of the other. So in bracket notation, it sends this ij matrix unit to I tensor j. That's the thing we have seen already many times. So why is this a tester? Let's compute this, this norm here. So what I have to do, I have to take a matrix X, and I have to compute the 2 norm of the output of this tester. So the 2 norm of the of vec of X, it's the sum of the absolute values of X squared, but it's also the matrix, the Schatten 2 norm of the matrix X, which is again the sum of the absolute value squared. And actually, you can show that these P norms, they are decreasing. So S2 is smaller than S1. So this shows that this condition here, the S1 to L2 norm of this map is satisfied. This is a contraction. So what we are doing here, basically, I mean, this VEC operation doesn't do anything. I mean, it just takes the wires and forgets about the tensor structure, right? So I'm back with the realignment criteria, right? So this is a general picture, but what I'm claiming that this operation VEC just takes the two wires and spits them like a big wire, but it doesn't do anything to the matrix. So you have this picture, and this again, it's row realigned. So this very simple operation gets you the realignment criteria. But then actually you can get many other criteria by modifying these maps T. So this was a very simple example, but for instance, if I take a map which just is given by this operation. So I have some matrices EK, and I'm taking the scalar product of these matrices EK with X. So basically I'm quote unquote measuring X in some basis EK, and this is the result. Then this gives you some other entanglement criteria which have appeared in the literature. So kind of this tester framework kind of unifies some entanglement criteria which have been studied. And the last thing that I want to tell you about these testers is that they're not so bad. So for instance, they can detect at least pure entanglement, meaning that if I have some multipartite quantum state which is pure and entangled, meaning that the storm is larger than 1, then I can find some testers, which unfortunately depend. So of course, they are not universal testers, so they depend on rho. But at least I can find some testers such that the entanglement of rho is witnessed by this criterion of using the testers that I described. So so this is like a general result, but I mean, for practical problems, you have to choose the matrices T depending on what you want to do. And if you have some prior information on your state rho, like symmetry or this kind of stuff, then you have to choose your T's accordingly. Good, so I think that's it. I'm a bit ahead time, but that's fine. Thanks so much for listening.
Thanks a lot, Ion, for the lectures. Any questions?
Is there a way to find these testers given density matrix rho?
No, I mean, I don't know. At least I don't know how to. So one way to think, I mean, one way that I like to think about these testers is like they play kind of the role of these entanglement witnesses.
Entanglement between them?
Entanglement witnesses. But as for witnesses, it depends. I mean, you have to find them case by case. I mean, there can, you know, yeah. And maybe for the same state, there are several choices of T's which make sense. It's no, there is no like systematic way. But you can incorporate some, if you know something about rho, like symmetry, you can incorporate them in the form of the tester.
Even for a pure state?
Sorry?
Even for pure state, can we find testers, certain testers?
You can try. I mean, you can try, for instance, you can try these vectorized testers, you can try some of which have this form. I mean, you can, whenever you have some, you think that some testers are good, you apply them to your state, you compute this smaller projective norm, and if you find that is larger than 1, then you're done. You have proved that the state is entangled. But if you don't find this larger than 1, then it has been useless. It's like all entanglement criteria. I mean, if they work, you are done. You have proved that your state is entangled. But if they don't work, you don't know anything. You don't know that the state is separable or entangled. It's only one implication.
Thank you.
Yeah, I had one question about I think I missed what this S1 to SK is. Could you explain that again? S1.
Where exactly? To which?
So in the subscript there is S1, right? So what exactly is S1 to SK? S1 is just a space?
Yeah, no, S1. No, S1, S1D. So this is the non-space where you have D by D matrices, complex, and the one norm, the trace norm.
I see.
So and it has two information. It has the size of the matrices and the norm you put on.
Okay.
So it's matrices with the one norm.
So it includes positive semi-definite as well.
I mean, positive semi-definite matrices are inside.
Yeah. Okay. Okay. Also, one more thing. So I noticed that when for pure state you had this injective tensor norm
Yes.
used for entanglement measure, but for this when you use draw it had like projective tensor norm.
Yes.
So what is exactly the relation? I mean I can't bridge between what exactly.
Well, I mean, it's completely different. It's really two different topics. There is no relation.
I see.
It's kind of strange that for pure states we have to use the injective one, and for mixed states we have to use the projective one. But you notice that also the spaces are not the same. So here we have projective of S1 spaces, and in the other case we have injective of L2 spaces. So it's really because also the tensors don't have the same number of legs. Rho has 2 k legs because it has inputs and outputs, and vectors just have k legs. They are just vectors. So it's a bit odd. I give you that. We also thought about this, but it is how it is.
Okay, thanks.
So in an earlier lecture, you used the trace norm, or the trace norm to define a notion of distance between
density
states.
matrices. Yeah.
Does it make sense to do the similar thing with tensor norms? Is there any interpretation of a distance between?
Well, I mean, that's exactly that. This number, so, you know, we have this characterization, right? So it's, so let's see, where is it? So this tells you that this trace norm, but this projective trace norm, where it keeps track of the tensor products, this tensor norm is 1 if and only if your state is separable. So in general, it's larger than 1. So the larger this norm is, the more entangled your state is. So as the injective norm defines kind of the distance between your vector and the set of separable states, this defines, in a way, it's not the distance to separable states, but it's related to that. I mean, it gives you a measure of entanglement. The larger this norm is, the more entangled your state is. So this is, again, it measures the distance between two states, but taking into account separability somehow. Right? If I don't want to take into account separability, I will just use the norm, which is S1, just one S1 space, and D1, D2 up to dk, right? So basically, I have this matrix, and I forget that. I put these two wires together, these two wires together. I forget that there is a tensor product. But if I want to keep track of the tensor product, which that's what separability is about, I have to use these tensor norms.
Okay, thank you.
I don't know if I answered your question or I was just rambling.
No, I think I get it. Thank you.
Yeah, I had a couple of questions. One was like, so you said that for mixed states with k equal to 2, if d1, d2 is less than equal to 6, then you can just take the partial transpose, and if it's not positive, then...
So if it's not positive, it's always entangled. This works all dimensions.
And
but if it's positive, I know it's separable.
It's separable.
Yes.
Only for d1, d2 less than equal to 6.
Yes.
So for 2 qubits, this would work.
For 2 qubits, it works.
But and it looks much simpler than, for example, something like concurrence, right? I mean, is in fact...
well, I mean, yes. So this thing, so concurrence gives you like a measure of how entangled, right? I mean, this partial transpose also, you can think it gives you a measure, but it's computationally they are the same because you have to compute some eigenvalues for concurrence. You have to compute the eigenvalues here.
So computational is the same. And does concurrence work even for d1, d2? It only works for...
For qubits, I think I don't think so. Yeah.
Okay. The other question I had was like, I mean, for...
But sorry, just to advertise, there is a talk on tomorrow. I don't know if Abbas is here. By Abbas, he will talk about some similar problems about entanglement and some symmetric states, and he will talk about states in small dimensions where this criterion fails. So if you compute the partial transpose, you see it's positive semi-definite, and the state is entangled. So so people are looking actively for these states because they have some uses in quantum information theory in cryptography and this type of.
Yeah, the other question was like for systems with, let's say, in the pure state with k equal to 3, so tripartite.
Yes.
I mean, so there, I mean, if it's entangled, or non-separable. I mean, is there a similar test like something like Bell's inequality which one can perform?
So for pure states, let me show you a formula at least. So the question for pure states, separability, it's an easy question. Why is that? Because you give me psi and you ask me whether it's of this form or not. So what you do is you take psi, I mean psi is something like this. Let's take 3, as you said. So if I want to check if this is product, so I want to check whether this is equal to something like this. That's the question. So what would you do? You would first cut here and look at this object as a matrix from 1 space to 2 spaces. If it has rank 1, it means that there is a cut here. If it doesn't have rank 1, you're entangled. And then you look at the second cut.
So I just look at all possible.
You look at, no, just 1, 2 cuts, so k minus 1 cuts.
Okay.
So because this matrix, when you cut it like this is called the flattening of your tensor, whatever. When you have this tensor and you put some legs as inputs and you keep the other ones as outputs, all these matrices have to be, if this is like this, all these matrices have to be rank 1, and it's a if and only if. So for pure states, deciding separability or not is easy. For mixed states, it's NP hard. Because here you see we don't have any notion of positivity, it's all about ranks. Whereas separability was, for mixed states, it was about positivity.
Thanks.
And this norm only tells you how far you are from this. But to say if you're like this or not, this is easy. But this tells you like how far you are from being separable.
Do we have any other questions? In that case, I suggest to thank Ion for the whole lecture course.